In this third video that we added just now, I want to explain some of the newer ways of doing variable selection in Pls Toolbox because there's a new interface that wasn't present when the original videos were made, and it makes life a little bit simpler. I'm gonna go with the data that we used in the other example, the beer data set. So spectral data, and let me just load in the calibration data, and I'm gonna load in eventually the extract that we want to predict. So here we have our spectral data. We have the visual area, which is hugely varying but not relevant for predicting extract. This part is relevant, but very small variation. And here we have very noisy variation, also at a very high absorbance value. So that's the data that we have to try to fix. Now, if I build a model, do 4, 5, or 6 components, I get fair predictions, as we already saw. Let me enlarge this one. So an error of about 0.7. The RMSEC is much lower, clearly indicating some kind of overfit. Could also be weird outliers or something, but in this case indeed, it is overfit. Now, there's this button here called variable selection. And if we go here, we have a set of different types of variable selection. So for example, there's one called variable importance. So that's basically using the VIP value that we have here. And what it's going to do is that it's going to try to remove the lowest fraction of VIP values and see if the model improves, if the cross-validation error is better. If it is, it's going to build a new model and again remove and continue removing as long as the predictions improve. And it's actually going to try with 10%, 20%, 30%, so different fractions, and then just pick the best model in the end. And we can hit this show plots and then press execute. And let's see what happens. So it's going to take a little while, depending on what type of pre-processing and cross-validation you've used. And I just realized now that I forgot to use mean centering. But it's probably going to work even though I'm doing the default auto-scaling here. We'll wait a little bit and then we'll see what happens. Once we've done with the calculations, this window, which is showing the average spectrum, is going to show which parts were selected, and it's also going to show me how well my model did compared to the original one, so I can assess if I would like to continue with this model. And we are close to being done. So we get a window here. In this case, the window is not particularly illuminating as we get more or less the same information here. But for some of the other types of methods, you're gonna really want to have this one open. Now we can see that it has selected variables in the right region, and it really improved the model quite a bit, down to 0.14, which is about as well as you can do on this data set. If I'm happy with this, I can say use, and that means that my variables here will be selected, the green ones will be selected, and all the other ones deselected. Let me try and do that. So what you see now is that only 52 variables are selected rather than all the 926. And I can try and redo the model now. I'm gonna go back here and I'm gonna look at my predictions. Right now I have a 3-component model. I'm gonna press here, press 1 to enlarge this window. And we can see it's doing quite fine. It doesn't actually say 0.14, it says 0.21. And that's a little bit interesting because the model we did seemed to indicate 0.14. Could be due to that I'm doing random cross-validation. But in this particular case, it's actually because the models were calculated with up to 20 components. And we get an error of 0.14 if we go out to very many components. If you look at the RMSE-CV here, you can see that it's actually lower here than around here, but I really don't want to go out here. I really want to stay around 3, 4, 5 components. So what you actually should do is that you should change the maximum number of components, and I typically set it just a little bit higher than what I'm interested in. Sometimes I even go a little bit lower just to force it to look at only the major parts. But in any case, I don't want it at 20 because when I'm doing the, let me show you here. When I'm doing this variable selection here, it really just tries to find the minimum among all the number of components that I have chosen in my cross-validation. Okay, I have to remember that I would also like to change to mean centering. That makes a lot more sense than auto-scaling on these data. Now, I would like to redo this trying with another method. In order to do that, I have to get my data back. I have to get all the excluded variables back. There are different ways I can do that, but one of them is I can just use my cache. If I look at here, I should have my original data in the original shape and form. So if I load the data now, let's take a look. Yep, now I have my original data back, and now I can try something else. So this was using variable importance, and variable importance is indeed a nice approach. It works particularly well when you don't have too much, let's say, irrelevant information. And let me show you how that is, because if I look at the VIP scores of my model here on the whole data set, I know that this is the interesting region. And you can see that the VIP is pretty good at removing noisy variables, but it gets a little bit confused in the visual area. So VIP is definitely a useful approach, but it's like all the other approaches, not perfect. It'll work well in certain cases and not in others. And it's not always easy to know when. With this particular data set, life is very easy. We know exactly what's going on. But for your own data, you may not actually know which method is going to be the better one. But what is kind of nice here is that we can always just try. And if it doesn't improve anything, we just don't go further with that. One thing that is important when using the VIP, of course, is that the model has to work initially. This first model has to work, because otherwise this VIP score is not going to be relevant. If the model is not predicting anything, that means my model parameters are nonsense, and so I wouldn't be able to look at this. So that's a prerequisite for the VIP scores. That also goes for the selectivity ratio, which is another similar measure. It's not the same measure. Basically what it does is that it tries to look at which variables are uniquely predictive of Y. So if you have a variable that's only reflecting Y, that would get a very high selectivity ratio. And as it turns out, that really works beautifully on this particular data set. It is not going to work nicely on any type of data, so it's not going to be your preferred method. That really depends on the type of data and your purpose. But for this particular data set. We can simply just remove the low values here, and we will have a perfect model. For less simple data, we could also do what we did before in the with the VIP. We could do that with the selectivity ratio, or we can actually combine them and simply look for the better one of both. So we can do the VIP and the selectivity ratio, and we can run them simultaneously. And now it's just gonna look for all these different fractions, first with the VIP and afterwards with the selectivity ratio. And what we'll find is something similar to before, maybe not with exactly the same variables, but with the same cross-validation error. And as stated earlier, that is really the thing that is important to remember, that variable selection does not aim at finding the same variables. It aims at finding the same predictive ability. But there are many ways to skin a cat, and so if one variable is correlated to another, you can pick one or the other and you're going to get the same predictive ability. So what you're mainly aiming at is getting a good prediction, hopefully with variables that you can interpret, but it may be other variables that are correlated to the ones that you can interpret. And you have to take that into account when you use your model, when you visualize your model and try to understand what's happening. I'm actually going to stop this now because I want to try some of the other methods. The results here are going to be similar to what we had before. So let me just stop that. Okay. Let me show you another one. We didn't manage to stop, so we got it here. We're not going to use these variables. They're kind of similar to before, and again we have a very nice low error, not exactly the same, but a nice one. I want to go on with IPLS. So if we do IPLS, let's see how many intervals. I often just aim at having around 30 intervals because it gives me a nice visualization. I do not worry about whether I cut in the middle of a peak or something like that, because that's generally not very important. I'm gonna find one interval. Let me show you what that means. We're just gonna start over. We're not gonna add to any previous selection. So I'm gonna say start over. And I basically am just doing a PLS model in each of the intervals. So that means in the first 30 variables. And if I do that in the first 30 variables, what I find is that my error is very high, above 2. And remember, the normal error is about 0.8. That's what we have here. And so in the whole visual area, I get really, really bad predictions. And now they actually get quite better. And when I go to this particular part, I get really nice errors around 0.2. And of course, if I go to the noisy region again, it gets really bad. Unless you have very many intervals, in which case there's no space, you can actually see how many components are used in the different intervals. And in the noisy area, we don't find more than one component, and then cross-validation says stop. In the systematic part, we can have more components, but only in the good areas do we get nicely predictive models. Now I can also add, so if this is a nice interval, I can look for which other interval to combine with this. And I can do that by simply saying execute and add to the previous selection. If we look here, the error right now is 0.18 using this one interval. And now I'm going to find the next interval to add to this one. So this is forward selection. That's just a neighboring one. That makes perfect sense. And I do get a lower error, so that's a good idea. We can also say automatic. And now it's just going to continue. I'm going to add to these two since they do make sense. And it's going to continue until the RMSECV doesn't improve anymore. And that might actually be now. It may be that we can't add more and lower. Maybe we can lower it a little bit. The time up here is how much PLS Toolbox estimates we need to spend if we have to add all the intervals. But that's hardly ever the case that we need that. Also not in this case. So apparently we can add another one and we get a slightly better error. Now, it doesn't really look like it's meaningful, but also if you remember, the error is not actually any different from what we had before. Before we had 0.15 with these two, and now we have 0.144. That's a very small difference. So in reality, we get the same predictive power with these two. And if I look at the regression coefficient of this model, then we're going to see that these ones, they don't really mean much, I guess. We can try. I'm going to say use these variables, and it's going to do so. So now we have 90 variables. Let me build a PLS model. And I need more than 3 components. Let me take a look. I'm going to go for 4 components. Maybe I should go further, but anyway, let me take a look. Let's see. Nice predictions. That's fine. Now let me look at the regression coefficients. So if I look at those, you see indeed that in the, let me just plot you the data. These are the data that we have selected, and I'm going to plot the excluded data so that you can see what part of the data we're looking at. Now, if you look at this, okay, we included this part, but it really gets very low regression coefficients. So that means it's mainly this area that matters, which is the part that we do believe is predictive. So including this area doesn't actually contradict anything that we know about the data. It's just a random little addition that marginally changes the RMSECV for these particular 40 samples. Oh. Let me close up this. And let me get back my original data again, because I want to try other types of cross-validation. Sorry, variable selection. So, let me build a model. Here we are. And let's actually just do the genetic algorithm. In the genetic algorithms, it's a little bit more time consuming. So what I'm going to do, what is really useful is to set the settings here, sort of close to what you think is the right settings. You can only choose between random and contiguous, and we definitely don't want contiguous here because the samples are sorted according to Y. So I'm going to go with random, and I'm going to go with, I don't know, 6 components. And something like this. Okay. Now I also have to define a window, and if you set it to 1, that means you have to check something like 926. Let's see now. I have 926 variables. That's a lot of combinations. So we want to lower that quite a lot. I'm going to put it at 30. What you really should do is try different ones, and you will hopefully see that as long as they're kind of reasonable, you get similar results. Okay, so I'm gonna press execute here. And now there's a window opening up, and it's gonna show me the results of what we're doing here. So it's calculating of the models of the first generation, and it's gonna show me how often different variables were selected in the 30 different wavelength regions. Region 1, which is this one, region 2, which is this one, etc. And we can see that all the variables, all the intervals have been selected more or less the same because they were randomly assigned initially. So there's not much structure to see here. But as soon as we get to, for example, the second generation, which will be coming shortly, maybe we will see a little bit of systematic behavior here. This is sort of the good region corresponding to where we have information about extract. And we already see a slight tendency to that region being overrepresented. Also, if I look at all the different models that were built in the second generation, in the first generation they had an average error of 1.2. Now they have an error of 0.8. And the best one has an error of 0.4. But here it has, at the third generation now, it has an error of 0.2. These ones, they don't necessarily go down monotonically, but we do want to see that they go down, both of them, that the models improve as we move along the generations. Over here I can see the fitness, so the RMSECV, as a function of how many intervals are in the model. That might not be so interesting always, but for certain applications this is nice to look at. Now you can see that at the fourth generation here, it seems that the noisy area, so that's this region over here, the noisy area seems to be sort of disappearing, and again the real important area seems to be very very often chosen. So there are many of the models in this generation that have this particular interval chosen. I'm gonna leave it running for a little while, so I'm gonna pause the recording and then come back when we are finished. Okay, it didn't really take too long. 10 generations, and now the genetic algorithm has stopped because not much is happening. And you see, we actually eliminated in sort of completely this noisy area. So none of the models in the last generation had this noisy region included. If you do this yourself, you will find slightly different results, but you will probably always find that the good region is very predominantly chosen. Now, here we can see the variables selected, and again we get a nice error about 0.2. Which is close to what we have before. If we're not really happy with this, where we can just select these variables and we can go back and to PLS and try and refine, and again we will see that especially this region is not actually very important. So it forms a nice basis for further refinement. I want to show you, we have this GA, genetic algorithm window, and that contains all the settings of the GA, which is kind of confusing at times, but we already explained those, and we normally don't use them too much. So that's why we have this simplified view that is normally fully sufficient. But there is this one particular button down here that I would like to highlight. If I push this one, I get a window that shows me all the models I made in the last generation. That's not so interesting in itself, but as stated up here, it says drag a box around the results, and that's what I'm gonna do. But notice that the different models have different RMSEC values. So what I'm gonna do now is that I'm gonna draw a box around them, and then I get this particular window. And this shows me, for example, that this interval was never chosen. This interval was chosen, but it was never chosen while the models were the best. These are the RMSEC values. All of them are nice actually, but these are the best ones. So these particular intervals, while they were chosen at times, they never were included in models that were good, which sort of indicates that you gotta get rid of these, and you gotta get rid of these. And actually, very often we would also have these ones being up here. But for my particular case, it actually turned out that the visual part was always in the good models. Well, was also in the good best models. This gives me a nice additional piece of information that can be very useful for interpreting my models and for further refining the models. Because you always have to remember that no matter what comes out of here is just a first rough guess. If it really does improve your model, that's nice, but you would typically want to go back into your normal interface and try and improve your models in here. And of course, in the end, when you're completely done, oh, this is not a nice model. Let me close this one because I have to have more components, 6 components, and then I get a nice model like this. And once we're done with our model, we should always test the predictions, because we've been fiddling a lot with the data. So we probably also risk overfitting and maybe cheating a little bit. So we really have to test that the model actually works on a new set of data. Let me just close this one and predict. Sorry, I didn't predict. So let me wait a bit. I'm clicking too fast. Here we are. So now we have a prediction, and let's see how well we actually do. Of course, we should check for outliers, but I'm not gonna do that at this point. Ooh, not nice. That's sad. So apparently this was not the nicest model. I also didn't optimize it very much. So what I will do now is that I'm gonna try and take a look at some of my diagnostics, like the VIP, like the regression vector, and like the selectivity ratio. Because here I know that I have a very sound model, because I already improved it quite a bit with my genetic algorithm. So it makes sense to say, okay, let me try and get rid of some of the variables that are not doing any good. Let's try again, and let's see how this particular model works. I'm gonna go with just 3 components, like this. I'm gonna take a look at my predictions. Let's see. Here we are. Much better. Much better.